Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 2, part of this playlist, Discrete Random Variables, and today's topic is Poisson Distribution. And the Poisson Distribution is the name for the French mathematician Simon Poisson from 1781 to 1840. Now, briefly, the Poisson processes follow these criteria: observing the number of events in an interval. And I put in quotes interval. It's often thought of an interval of time, but it doesn't have to be. It could be the number of calls in a 1 hour time period. Could be the number of bacteria on a drop of blood. So then the drop of blood becomes the interval in quotes. Let X be the number of events observed within the interval. The parameter lambda of the Poisson process represents the number of occurrences of the event per measurement unit. And I'll give an example later to illustrate that. Then the density of X is a Poisson distribution given by this function, f of X given lambda, e to the minus lambda, lambda to the X divided by X factorial. X can be from 0 to infinity, right? The number of events within that interval could be 0, could be 1, could be 2, all the way up to infinity. Now we're going to use this Maclaurin series for e to the X several times in proofs in the upcoming, so I wanted to put it as a reminder. Let X be a Poisson random variable with parameter lambda. The mean of X is given by lambda. The proof is this: expected value of X is X times the density summed over all possible values. Plug in the density. Now notice when X is 0, this term is 0, so it doesn't add to the sum. So we might as well start at 1. We're going to take out e to the lambda because it's not indexed, and we're going to take out one of the lambdas. And now we're going to do an index substitution. Let y equal x minus 1. Then this sum becomes this one. But this is a Maclaurin series about e to the x with lambda replaced with x. So we get this expression, it's e to the lambda. Those cancel, or, leaving 1. So 1 times lambda is lambda. That's what we wanted to show. Let X be a Poisson random variable with parameter lambda. The second factorial moment of X is given by this. Expected value of X times X minus 1. Now, on a side note, the third factorial moment would be expected value of X times X minus 1 times X minus 2. But here we only need the second factorial moment. We can multiply the X in, take the expected value of each, and that's lambda squared. And the proof is this: expected value of the second factorial moment, take X times X minus 1 times the density, and we get this. Now notice that when X is 0 or X is 1, the terms are 0, so we might as well start at 2. And then the X and X minus 1 cancels with some of these X factorials. We take out the e to the lambda, take out 2 lambdas, re-index it, y equals X minus 2. This is Maclaurin series about e to the X, but with lambda replaced by X. That's 1 lambda squared. Let X be a Poisson random variable with parameter lambda. The variance of X is given by lambda. And here's the proof. Variance of X is equal to the expected value of X squared minus the mean squared. That's by definition. Let's add 0, add and subtract the mean, the same quantity, so it doesn't affect it. But the term on the left is the second factorial moment, and the other two terms come down. Plug in what we know. X lambda squared plus lambda minus lambda squared is lambda, and that's what we wanted to show. Let X be a Poisson random variable with parameter lambda. The moment generating function of X is given by this expression, e to the lambda times e to the t minus 1. The proof is this: the moment generating function, m of t, is expected value of e to the tx, plug in e to the tx times the density, summed over all possible values, and plug in the density. Now what we're going to do is take out e to the minus lambda because it's not indexed, and then we're going to join e to the tx with lambda to the x here. Well, this is a Maclaurin series about e to the x with lambda t to the x replaced in place of x. And we get this, e to the lambda e to the t. We can join those into this expression, and that's what we wanted to show that the moment generating function is. Now notice this form of the moment generating function. If two moment generating functions are equal, it says that their densities are equal. So let's let xi be independent Poisson random variables with parameter lambda I, where I goes from 1 to n. The moment generating function of x, which is the sum of these independent Poisson random variables, is given by this expression, where so it's a Poisson, it has the same form as a Poisson, a moment generating function from a Poisson distribution, but lambda is the sum of the independent Poisson random variables, the sum of the lambda I. And let's prove it. Now we're going to use theorem 6 from video ims15, and this means the 15th video in the playlist Introduction to Mathematical Statistics. It's about moment generating functions. So the moment generating function of x is expected value of e to the tx, but according to theorem 6, that is the product of the individual random variables. And since each of these are Poisson random variables, it's this, with parameter lambda I, and we're taking the product from 1 to n, so this times, plug in 1, then 2, then 3, and you get this expression. But this is what we wanted to show, right? So it's, again, a Poisson random variable. Now, example, suppose that the number of defects on a bolt of cloth produced by a certain process has a Poisson distribution with mean 0.4. Now that's our lambda, and notice it's not an interval of time. We're just talking about a bolt of cloth, and there's 0.4 defects on average on a bolt of cloth. So lambda is 0.4. If a random sample of 5 bolts of cloth is inspected, what's the probability that the total number of defects on the 5 bolts of cloth will be at least 6? So now we're taking 5 bolts of cloth, right? So we're going to add 5 bolts of cloth together, and each one of those has a Poisson process. So we add the lambdas, but in each case it's the same lambda. So the answer is this. So let x be a Poisson random variable with mean 5 times lambda, right? Because we're now adding the 5 bolts of cloth together. Each has a 0.4 mean of defects. So it's a Poisson random variable with 2, 5 lambda is 2. So we want the probability that x is greater or equal to 6. And that means we sum the density from 6 to infinity, which would be tough. So we take 1 minus x is less than or equal to 5. And this is something that we can easily sum. It goes from 0 to 5 of the Poisson density. Some call it a probably mass function. Both are okay. It's a density of what's called the discrete type. This is 0.98. 1 minus it is 0.0165. Now let's do these calculations in R 3 different ways. One, we're going to use the density of a Poisson distribution. We're going to find the density for values 0 through 5. Lambda parameter is 2. We want to add those up, take 1 minus it, and we get the same value. We can use the CDF function, which is P. If it's a D in front, it's density. P is the CDF. And then we take 1 minus the CDF, but we're going from 5 and less. Lambda is 2. We get the same value. But we can also use the CDF, but take the upper tail as opposed to the lower tail. And so we say P Poisson 5 and 2, but lower tail is false, means we want the upper tail, and we get the same quantity. All right, well, we're at 10 minutes. I'm going to end this video. Hopefully you enjoyed that. I sure did. In the next video, we're going to start continuous random variables. So please subscribe, like the video, and see you next time.